Let us learn today about transformations. What are transformations? The manipulation of objects in space on computer. It is simulated. This is called as transformation. That is the manipulation of object and in space as simulated on computer is transformations. For example, we use the transformations for applying motion to different parts of the robot. That's why it is considered as a module for robotics. It is also applied in computer graphics. The basic fundamental concepts are based on linear algebra. That's why it finds wide scale applications in other fields as well. We are going to learn it on the viewpoint of CEM, Computational Engineering Mechanics. So let us learn transformations. Broadly, transformations can be categorized as two types, that is 2D and 2D geometric transformations, 3D geometric transformations. That is about geometric transformation. Other part is coordinate transformations. So transformations broadly two types: geometric and coordinate. Then geometric again into two types: 2D and 3D. In the same way, coordinate also can be subcategorized into 2D and 3D. Now, what is this concept? Let us understand. Suppose automobile is moving on the road. We want to simulate the motion on computer. It can be achieved from two viewpoints. One, you keep the background fixed and give motion to the automobile. That is, you move the object relative to the fixed coordinate system. Motion is applied to the object and not the coordinate system. The background is still and the object is moving. So this is the case of geometric transformation. And the other is coordinate transformation. The background is moving, the object is stationary. So because of the motion of the background, it appears as if the object is moving. So this is the second viewpoint, that is coordinate transformation. Out of these two, we are going to learn about geometric transformations only. Coordinate transformations is not in your syllabus. It is out of the scope. That's why we will focus on geometric transformations, wherein the object is given a motion to the object. We give the motion to the object and the background is hold stationary. So there are various types of geometric transformations again, 2D as well as 3D. Broadly, we are going to learn about four types, that is translation, rotation, scaling, mirror reflection. These four transformations are also possible in 3D. We are not going to deal with any numerical on 3D geometry transformations, only we will learn about the fundamentals. Whereas for 2D, we will solve some numericals also based on all of these four transformations. Let us consider the first one, translation. What is this? Translation means we move the object along a path, that is translate along a vector. So just understand this with the help of the sketch. Any object is composed of points. So let us say we have an object obj and point P is a part of this object. We will move this object along a vector v so that P is translated to P dash, and in the same way all other points are also given the same motion, so the object becomes obj, that is the new position of the object. Obj is obj dash. Similarly, the new position of point P is P dash. This is translation. So the vector v is given by txi plus tyj. So new position of point P is P dash. So we apply the transformation TV, that is a symbol for translation, to point P, and we get new point P dash. In this case, x dash is x plus tx and y dash is y plus ty. We will solve some numericals later. So this will be more clear in the numerical. So we are simply migrating the points, all the points of the object to new location along vector v. This is translation. Now let us see the second transformation, that is rotation. Just try to understand this with the help of a sketch. So here we are rotating the object in anti-clockwise direction by angle theta. So this is denoted as r theta. That is, r stands for rotation, theta is the angle of rotation. So the point P dash equal to r theta P. P dash is the new position of point P. I by applying the rotation transformation r theta. Here x dash equal to x cos theta minus y sin theta, and y dash equal to x sin theta plus y cos theta. Let us learn about third transformation, that is scaling. scaling with respect to origin. Let us say we have a rectangle. Point P is a point of this rectangle. We apply the scaling transformation. It is denoted by S, Sx, Sy. Sx is the scaling factor along x and Sy is the scaling factor along y direction. In this example, we are enlarging the object along x by factor 2 and we are reducing it along y by factor half, one half. So here expansion along x and compression along y. Just note that when we perform scaling transformation, the location of all the points will also change. So only the origin will remain same. All other points on the object will be shifted. So scaling is simply not enlargement or reduction. It is look changing of location also. So translation is involved in scaling. The scaling transformation is said to be homogeneous or uniform if S is greater than 1. It is a magnification, and for S less than 1 it is a reduction. When both when both scaling constants have same value S, then the scaling transformation is said to be homogeneous or uniform. It is magnification when S greater than 1, and a reduction when S less than 1. Another transformation, that is a mirror reflection. Mirror reflection about x axis or y axis. Here the x-axis is acting as a mirror. So let us understand with this sketch. Here x-axis is acting as a mirror. So point P will have a reflection and new position P dash x dash y dash. In this case, you will see that x dash is equal to x and y dash is equal to minus y. So, in mirror reflection about x, there is a change in y coordinate, whereas x coordinate remains the same. Now, other mirror reflection is about y. You will note that x dash is minus x and y dash is y. So when you take a mirror reflection about y axis is treated as a mirror, and in this case the x coordinate is reverse, is negative, and y coordinate remains the same. So x dash is equal to minus x, y dash is equal to y. We have the notation for these transformations. P dash is equal to mirror reflection about y axis of P, and in the previous case we can write here P dash is equal to mirror reflection about x of P. The notation is mx. And for mirror reflection about y, notation is my. You'll observe that mx is also represented as scaling with a factor 1 comma minus 1, and my can also be represented as scaling with a factor minus 1 comma 1. So we can treat the mirror reflection as special case of scaling. So we have learned all the four variations of 2D geometry transformation. Now let us learn about inverse geometric transformations. Each geometric transformation has an inverse, which is described by opposite operation performed by the transformation. For example, translation, inverse denoted by TV inverse is equal to translation in opposite direction, that is T of minus V, or translation in opposite direction. Then inverse of rotation, denoted by R theta inverse, is same as rotation in opposite direction, or R of minus theta, that is rotation in opposite direction. And scaling inverse denoted by Sx comma Sy inverse is S 1 upon Sx comma 1 upon Sy. Whereas mirror reflection inverse of mirror reflection about x, that is mx inverse is mx, and my inverse, that is inverse of mirror reflection about y, is equal to my. We will use these inverse geometric transformations when we consider matrix multiplication or composite transformations. Let us learn more now about homogeneous transformations. If you see the notes, wherein you will find the next point as coordinate transformations, all the four types, that is translation, rotation, scaling, and mirror reflection in coordinate transformation. Since this is out of the scope for your syllabus, from your syllabus, you can skip this point and directly jump to the next point, that is composite transformations. The next point here is composite transformations. So let us learn about this composite transformations. Composite transformation is nothing but combination of multiple transformations. So complex geometric and coordinate transformations can be built from basic transformations by using the process of composition of functions. For example, rotation about a point other than origin. Or reflection about lines other than axis. Or scaling the object with respect to one of its point. Let's say center. So X Sy with respect to the center of the object. We want the center to remain in the same location as previous location, but the object should be scaled along x and y direction. That is the meaning of this. It won't happen in a simple transformation. We have seen that when we do scaling, all the points of the objects are shifted. So scaling is itself a composition of translation and scaling. Is not a simple transformation. So if we want to keep the center fixed, then first we will translate complete object along with the center to the origin, then scale it with respect to origin, and then translate it back to the original position. So it is a composite transformation. So let us see this example. Scaling of the object, keeping its center fixed or with respect to its center. So it is represented by, say, suppose C is a center having coordinates h and k. We choose a magnification factor, that is S is greater than 1, and construct the transformation by performing the following sequence of basic transformations. A uniform scaling factor greater than 1 in both direction, Sx is same as Sy. So we just use a simple term S, that is a uniform scaling factor greater than 1. So we do the sequence, translate the object, so that its center coincides with the origin. Then next step, scale the object with respect to the origin, and translate the scaled object back to the original position. The required transformation S S comma C can be formed by composition T inverse TV inverse S S S S is uniform and back to original position T of V, where V is nothing but translation vector HI plus KJ. Let us see this graphically. Let us say we have a square with the center H comma K, and we will scale it keeping the center fixed. So first step is align the center with the origin, that is inverse translation. This is the first step. We align the center of the object with the origin. Then second step, apply the scaling. So we are enlarging this. We apply the scale here. And lastly, we will again translate the center back to the original position. So this enlarged object is again shifted to the original position of the center. This way we achieve the scaling with respect to the center. T of T inverse of E, that is shifting the object center to the origin, shifting the center to the origin. This is the first step. Then scaling with respect to origin. This is the second step. And lastly, shifting the center back to the original position. Now let us learn about the matrix form of these transformations. Matrix description. Rotation. R theta is represented by a matrix 2 by 2 matrix. Cos theta, sin theta, minus sin theta, cos theta. Then scaling. It is represented by a matrix Sx0, 0 Sy. Then mirror reflection about X. The matrix form is 1, 0, 0, minus 1. Mirror reflection about Y. Matrix form is minus 1, 0, 0, 1. What about translation? Translation cannot be represented in a 2 by 2 matrix. For that, we need to learn about a concept of homogeneous transformations. What is homogeneous coordinates and homogeneous transformations? Let us learn about that. This is the concept of projective geometry. We have a point P, X, comma Y in 2D Cartesian form, as p x comma y comma 1 in homogeneous coordinate form. Or a point p x comma y comma w in homogeneous coordinate equal to p x by w comma y by w in Cartesian form. Actually, in 2D x comma y is on z is equal to 0 plane, but we project that to z is equal to 1 plane. That becomes homogeneous coordinates. In the same way, p x comma y comma z in 3D Cartesian form is equal to p x comma y comma z comma w, or say 1. W can be anything greater than 0. So let us say x comma y comma z comma 1 in homogeneous coordinate form. Or p x comma y comma z comma w in homogeneous form is equal to p x by w comma y by w comma z by w in 3D Cartesian form. Alright, now what are the advantages of this homogeneous coordinate form? Advantages of the homogeneous representation. Number one, the two-dimensional transformations can be represented as a 3 by 3 matrix. The two-dimensional transformations can be represented as a 3 by 3 matrix. Second, floating point arithmetic can be avoided. For example, a point P 1 by 2, comma 1 by 3 in 2D can be represented as P 3, comma 2, comma 6 in homogeneous coordinates. And translation in the direction V equal to Txi plus Tyj can be expressed by TV equal to 1 0 0 0 1 0 TX TY 1. So it is expressed as a 3 by 3 matrix. Then let us understand multiplication of x comma y comma 1 with this matrix. This is homogeneous form of the point x comma y, homogeneous form x comma y comma 1, multiply with this 3 by 3 translation matrix. So this will give us the result x plus tx y plus ty 1. From this we can easily decode and y equal to that's how we got translation in 3 by 3 form, and we can multiply that with the homogeneous coordinated form of the point and get the result. In the same way, rotation matrix r theta can be expressed as cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So this is a 3 by 3 matrix for rotation. Now let us apply this rotation transformation to the homogeneous coordinate of a point P. P dash is equal to r theta P. Therefore, homogeneous coordinate form for point P is x y 1. Multiply this with r theta matrix, cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. This is the homogeneous matrix in the homogeneous form for r theta. Multiply these two, so we will get the result as, I'll write here, x cos theta minus y sin theta, then x sin theta plus y cos theta, and 1. So this is matrix multiplication. From this we can easily decode x is equal to x cos theta minus y sin theta, and y is equal to x sin theta plus y cos theta. So this is a homogeneous form, and we can reduce the 2D Cartesian form. So x is equal to x cos theta minus y sin theta, y is equal to x sin theta plus y cos theta. And in the same way, scaling transformation in homogeneous coordinate form becomes S of Sx comma Sy is equal to Sx 0 0 0 Sy 0 and 0 0 1. So x y 1, that is the homogeneous form of the point P x comma y, multiplying this with the scaling matrix, this will result in x into Sx, y into Sy 1. So from this we can deduce x is equal to x into Sx, y is equal to y into Sy. Now let's move on to another point now. Let us take the example of scaling, keeping the center fixed. So scaling S S comma C. Let us consider the example. Let us solve this problem of scaling the object with respect to its center. What does this mean? This means that we have to scale it keeping the center fixed. We have learned that this is a composite transformation, inverse translation, that is translating the object such that the center coincides with the origin, then scaling it about the center, about the origin, and translating it back to the original position. So this is expressed in the matrix multiplication form. Minus h minus k 1 minus, because we are doing inverse translation, migrating the center of the object to the origin. So h becomes minus h, k becomes minus k. Now here with this the center will coincide with the origin. T v inverse, then scaling with respect to the center or scaling with respect to the origin. Now s 0 0 0 s 0 0 0 1, and again translating the center to its original location. So 1 0 0 0 1 0 h k 1. So let us do this multiplication step by step. First, multiply matrix 1 with matrix 2. S 0 0 0 S 0 minus HS minus KS 1, and multiply this with the third matrix 1 0 0 0 1 0 H K 1. This is giving us the final matrix S 0 0 0 S 0 minus hs plus h minus ks plus k 1. This is about all about composite transformation. Now let us learn one more transformation, that is a shear transformation. X shear and Y shear. The shear transformation causes the image to shear or slant. X shear maintains the y coordinates, but changes the x values, which cause the vertical lines to tilt left or right. Let's see this graphically. The object is L-shaped object. we are applying X here. Here Y coordinates remain the same. There is a change in X coordinates. The horizontal lines will remain horizontal and vertical lines will tilt towards right or left. You can see X coordinates are changing. Okay, so horizontal lines, the dimensions will change, but they will remain horizontal. Whereas vertical lines, the length of the vertical lines will remain same, only it will tilt towards right or left. So now this X here is nothing but a combination of rotation and scaling. Okay, it's a composite transformation. We can write this in the matrix form. In homogeneous matrix form, S Ajax, that is X shear, the Y levels are maintained, X will change. So horizontal lines will remain horizontal but dimensions will change. Vertical lines, the dimension will be same but rotation, it will cause a rotation of the vertical lines towards right or left. So S Ajax is 1 0 0 A 0 0 0 0 1, where A is the X shear factor. In the same way, the Y shear will preserve all the X coordinates. But shift the Y coordinate. This causes horizontal lines to transform into lines which slope up or down. Let us see this graphically. We'll take the same example of L-shaped object. And now apply Y shear Y shear is preserving all the x coordinates and there is a change in the y values. So vertical lines will remain vertical, dimensions will change. And horizontal lines, dimension will be same but they will slope down or up. And homogeneous coordinate matrix form. SHY equal to 1 B 0 0 1 0 0 0 1. Where B is Y shear factor. It is possible to form shear transformation using the transformation of rotation and scaling. It is also possible to form the shear transformations using transformations of rotation and scaling. That's all for today's discussion. Briefly, let us revise what we have learned. We have learned about different types of transformations and the subcategories of these transformations: geometric transformations, coordinate transformations. Out of these two broad categories, we focused on geometric transformations. Again, two types, 2D and 3D. From this, we have focused more on 2D geometric transformations, four types: translation, rotation, scaling, and mirror reflection. And we had seen the matrix form of these transformations. We had learned about homogeneous coordinates and inverse geometric transformations. Also, we had learned about shear transformation. Thank you for being patiently